A crystal ball and a chili cook-off, a data analytics analogy. So let's imagine that you're trying to win your neighborhood's chili cook-off this year. And there's a crystal ball that will tell you what the perfect recipe is for winning that pot of chili. A data model is like creating a crystal ball that will tell you which combination and quantity of ingredients will produce an award-winning recipe. The features are the ingredients, the label is the chili recipe, and the model is the crystal ball. Now, those chili ingredients are stored in a fridge or pantry, just like data is stored in a data warehouse or database or Excel spreadsheet. And then data cleaning is like prepping the ingredients before using them in the recipe. So tomatoes need to be washed, beans need to be soaked, and onions need to be peeled. In the same way, raw data often needs preparation before it can be used effectively in models. So after the ingredients are prepped, we take them and we run them through the model, the crystal ball. And the crystal ball tells us what's going to make that winning pot of chili. So the crystal ball can use Excel, or it can use Azure ML Studio, or it could use another tool. We're just trying out different types of crystal balls. And in each case, we're trying to predict what ingredients will make the best chili recipe. Now that we've run the model, the next thing is to judge it. And that's what all those stats like R squared, P value, T stat, all that are. And I'm going to share with you how I remember those because it's a lot, right? All right, I think of R squared as like the percent of the crystal ball that is clear enough to see through to the winning recipe on the other side. The values are between 0 and 1, which means that you can think of them as percentages. So a 0.00 R squared value means that you can see 0% through the ball. It is 0% good at predicting. 0.1 means that you can see 10% through the ball. Not great, but better than 0. 0.5 means you can see 50%, and 0.75 means you can see 75% of the way through the ball. These models are rarely, if ever, going to be 1. There's like no 100% certainty, and that's okay, because much of the value of these models come from analyzing the predictions about each feature or ingredient and how it impacts the label or the winning recipe. It's this analysis that helps form business decisions. So here are 3 of the stats that we use a lot, and this is how I remember them. So coefficient is like the slope of a roof. For every 1 unit, the feature quantity increases, the label increases or decreases by the amount of the coefficient. So if the coefficient for salt was 6 and the unit of measure was teaspoons, then for every 1 teaspoon of salt, the chili would increase by 6 levels of winningness, whatever the unit of measurement is for that label. So like if the label was to predict the cost of the chili, then for every 1 teaspoon of salt, the chili would increase by $6. Now, the T-stat is the effect size. I envision a Venn diagram. The effect size is where the 2 circles overlap. And 1 circle is the feature and the other one is the label. For example, if you put 1 tablespoon of cayenne pepper in the chili, it's going to have a much larger effect than putting 1 tablespoon of tomato paste. Even a tiny amount of cayenne pepper is spicy, so a full tablespoon would be very hot. Whereas you probably wouldn't even notice if you added 1 tablespoon of tomato paste. So tomato paste is likely to have a much smaller effect size than cayenne pepper. P-value is the likeliness that the results for this feature are due to chance. Is it random that adding more salt makes the chili saltier? No. There is 0% chance that the increased saltiness is a fluke. So 0 is good. That's what we want for p-values. 1 means there is a 100% chance that this is random. You might as well roll the dice when making this choice because it has no predictable impact on the outcome. Now, the p-value and the R squared both have values of 0 to 1. But with R squared, the closer it is to 1, the better. With the p-value, the closer it is to 0, the better. Because an R squared close to 1 means you can predict with 100% accuracy, and a p-value of 0 means there's 0% chance that's random. So a model with a high R squared and a low p-value means that this model is going to be really good at getting you to win the chili cook-off. By the way, R squared has a p-value, and it's the significance of F metric that we would see in the ANOVA in Excel. All right, now let's talk about errors, or rather the difference between what you predicted and what actually happened. So these are tricky to understand. I hope this helps. Think of the mean absolute error, MAE, as a taste test. So once you've served the chili, you expected the chili to taste one way, but it tasted different than when you expected. Perhaps you predicted that you only needed 1 onion, but it wasn't oniony enough. To get it to taste like what you wanted, it needed 4 onions. That would be an error of -3 because the actual value was missing 3 onions. But we take the absolute value because you can't actually have negative onions, though some people wish they could. And then you do this for each feature and average them all to get the MAE. For the root mean squared error, RMSE, you take those same values and you square them all before you average them. So if the ingredient was off by 1, the effect size stays the same, but when the onion error is squared, it becomes 9 instead of 3. So the effect size has tripled. And this helps you to find the worst errors because it gives more weight to big errors so that you pay attention to the fact that you should not leave out so many onions in the future. Okay, every time skewness comes up, I need a refresher, so here it is. Skewness only applies to numerical features, not categorical ones. Linear regression models assume a normal distribution in the data set for a feature. In other words, it expects the data points to be evenly spread across a lovely bell curve. So if the data isn't that way, if it's skewed, it decreases the predictability of the model. So positive skew is right skew, and it means that the hump is on the left and the tail is on the right. That's so backwards to me. I try to remember that the name of the skewness is about where the long skinny tail is, not the big hump. So negative skew is left skewed, and it means the hump is on the right and the long skinny tail is on the left. In Azure Machine Learning Studio, we're creating pipelines and jobs, and I just thought this would be helpful. A pipeline is like a workflow, and a job is like an order to run the model. So if you were in the kitchen, the pipeline would be like everything you have to do to make a pot of chili, and a job would be an order for a pot of chili. Also in Azure, we had to insert a pill to split the data, so I asked ChatGPT to explain this in this metaphor. So here it is. So we split the data to improve testing. So imagine that you have a group of friends that have gathered to help taste test as you develop the perfect chili recipe. And instead of testing on the whole group at once, you split them into 2 groups. So you have the training group, the first group, and they help you develop the recipe. You experiment with different spice levels and adding more chili powder or cumin, and you figure out what works best. Okay. This also trains the trend line if we were looking at a chart. And then you have the second group, the testing group. So once you think you've got a solid recipe, then you serve the chili to the second group who didn't taste any of the earlier experiments. They only taste the final version. And then this group plots the points. So their reactions show whether the chili is too spicy, too mild, just right. And by splitting the testers into these 2 groups, you get a much clearer picture of whether the recipe will work for a broader audience. And the testing group ensures that you're not just making chili that works for the people who happen to help you create it, but one that fits real world tastes. Okay, so this is my cheat sheet. These are the images and words I visualize in order to keep all this straight in my head. So it's just a quick review. So R squared is the percent that I can see through the crystal ball. It's how good the model is at predicting. The coefficient is the slope of the roof. For every 1 unit of feature, the label moves 1 unit. T-stat is the effect size. It's the overlapping area in my Venn diagram. P-value is the percent that this is chance. I want it to be as close to 0 as possible. MAE is the average of the mistakes I made in the taste test. RMSE highlights the worst mistake I made in the taste test. And skewness is backwards from what I think. Right skewed has a left hump and left skewed has a right hump, and normal has a hump in the middle. That's it. I hope this is helpful for you. If not, it was helpful for me to write this all down and visualize it. If you're still with me, thanks for watching. I am sending you good wishes. May your data be clean, your R squared be clear, and your p-value never left to chance.